Hey guys, welcome back. My name is Mr. Kim, and today I'll be going over the June 2023 Regents Chemistry FRQ questions. Let's get started. Question 51. The element technetium, Tc, has several isotopes. The bright line spectrum of technetium has been observed in the spectra of some stars. Compare the energy of an electron in the first shell of a technetium atom to the energy of an electron in the third shell of the same atom. So we're looking at the energy element in the first shell versus third shell. And what do we know? We have the nucleus and you have the first shell, third shell. This is higher energy, right? Because remember, when electrons get excited, they move to higher orbit. So what you're going to write is up. The electron on the first shell is of lower energy than the electron on the third shell. Okay. All right, let's go to 52. State in terms of protons and neutrons why the various nuclides of technetium are isotopes of each other. So you understand this has absolutely nothing to do with technetium, and it also has nothing to do with bright line spectra. And I know a student might ask about bright line spectra. You guys remember bright line spectra is the thing we saw where if you look through the spectroscope at different elements, that glass light-looking thing, the lab we did, it gives you different lines at different colors of the rainbow. Well, remember, for future reference, these lines are the light that's released when excited electrons come back from a excited orbit. But that being said, if you look at 52, it has nothing to do with bright line spectrum, nor does it have anything to do with technetium. It's just asking why, what the difference of isotopes are, right? So what are isotopes, right? So we know that different isotopes have, now remember, it says in terms of protons and neutrons, so you have to include that in your answer, right? Have the same numbers of protons, but different numbers neutrons. Okay, well, let's continue. Let's go to 53. Looks like 53, they want us to draw something. So let's go take a look. A sample of gas in a sealed rigid cylinder with a movable piston has a volume of 0.250 liters at STP. And this is what? This is volume, right? And this is at STP, which means what? You have temperature and pressure that's available. Show a numerical setup for calculating the volume of the sample of gas at such and such. So what do we got? We got our first conditions and we have our second condition. So this is also temperature and this is also pressure. But what are we looking for? We're looking for second volume like that, right? So where do we go first? If you don't remember your combined gas law, right? You should, right? From beginning of the year. Go to the equations page and then you have your gas laws, combined gas law right here. Right? Oh, sorry. Right here. That's your combined gas law. Okay. So we need PVT, PVT 1 and 2s, right? So let's set that up, right? Let's set it up right here. P1, V1, T1, P2, V2, T2. In fact, you know what? You can go do the work over here too, right? You can do it here. P1, V1, T1, P2, V2, T2. Okay. We're looking for our V2, right? So let's get some values now, right? So it says our volume initially is 0.250 liters, right? So I'm going to write that down, 0.250 liters, right? And then we have at STP. So what does that mean? If it's STP, right, some of you should know value, right? It's 1 atmospheres and 273 kelvins. But if you didn't, it is right here, right? It's 1 atmospheres and 273 kelvins. Okay, so let's go. Now, why are we using those two values, right? Because if you go to the problem, we are using kelvins and atmospheres, right? So from this page, you copy down, pressure is 1 atmospheres and temperature is 273 kelvins. And then for our P2 and V2, we go back to the problem and we got our P2 and we got our T2, okay? P2 is 298 and P2 is no change. So there's two ways to solve this, right? You could go ahead and just plug everything in and go P1 V1 over T1 equals P2 V2 over T2, right? We're solving for V2, so we can say V2, and let's consolidate all our guys, right? So it's going to be like this, right? Like that, okay? Now, plugging in our values, we got 1 atmospheres times 0.250 times T2, 298 kelvins all over. T1 is 273 kelvins, and P2 would be 1 atmospheres, right? Now, this is the correct answer, but I'm going to pick a different color and tell you how an alternative way to do this, right? The alternative way to do this is understanding that our pressures are the same to each other, which means that they cancel each other out. So essentially, if I start over, right, like that, we know that P1 and P2 are exactly 1 atmospheres each, and they cancel out. And it actually makes the equation a lot simpler, doesn't it, right? So and that means that V2 is equal to V1 over T1, right, times T2, right? And then what do we get? The setup would be 0.250 liters times, what is T2? T2 is 298 kelvins all over 273 kelvins, right? This would also be a correct answer, right? And if you notice that the difference between the one working blue and the green, the 1 atmosphere is redundant, okay? So either one works. But if you can understand, the green way is actually faster, right? Okay, let's go to 54. State a change in pressure that will cause the gas in the cylinder to behave more like your ideal gas. Now remember, ideal gas means what? Okay, you got to remember that and memorize this. Ideal gas is when gas molecules move apart, right? They need to be as far apart as possible. That's when real gases behave ideally, right? All right, so how do you do that in terms of pressure, right? If you increase pressure, what are you doing? You're squeezing gas molecules together, and that's no good, right? We want the gas molecules to move apart because that's how real gas acts like an ideal gas. So what we want to do with pressure is we want to separate the gas, right? So what you want to do is you want to decrease the pressure, right? So this would be increasing pressure. This would be decreasing pressure. And that's the effect it's going to have, right? So you would say decrease. Oh, I should change in blue, but I like this color. The pressure. Okay. Also, just understand in terms of temperature, right? How would you affect the temperature if they asked you about temperature? Well, if you heat gases, they expand and move further apart from each other, right? So an ideal gas or a real gas behave ideally at low pressures and high temperatures. All right, let's keep going. So let's go to 55. During laboratory activity, a student heats beaker containing 120 grams of water as shown in the diagram below. The table below shows a mass of the water and the temperature of the water before and after heating. During the laboratory activity, appropriate safety equipment, whatever, okay? 55, state the direction of heat flow between the candle flame and the beaker of water during the time the candle is lit. Again, this has nothing to do with laboratory activity. It's just asking you, right? If you have a candle and a beaker, which direction does the heat go? Now, believe it or not, kids get this wrong, but where does the heat go? Heat goes from here, right? Into it like this, right? So from candle flame to beaker, right? Is the answer. If you wrote candle to beaker, I think it's acceptable. It should be. Right, so let's keep going. 55. State the, oh, hold on, what just happened? Yep, so 56. Show a numerical setup for calculating the amount of heat in joules. All right, so amount of heat, what's, it's a unit for, symbol for heat is Q, right? Absorbed by the water, so it's just water, okay? That's important. The beaker is the result of the burning candle. All right, so what information we got? We got information up here. Let's go take a look. We got mass. And what do we got here? We got TF, final temperature, and initial temperature. And what does that give us? That gives us delta T, right? You guys remember what delta T is? What do you think? Right? It's TF minus TI, right? You got to remember that. You got to memorize that, please, okay? All right, so let's go. So now we can figure this out, but you're thinking, hey, where do I get the equation? Well, you guys know what the equation is. We already talked about it. Q equals MCAT. But if you don't remember that, again, just go to your chart. Again, try not to go to this chart as much as possible, right? By memorizing some of this stuff, right? Q equals MC delta T is right here, right? Now, how did I know to use that? Because I saw there's delta T and there's M, right? So let's go and set this up. Now, double check. Do they want numerical setup? Yep, they want numerical setup. Now, you can write the answer, and that's fine. But the problem is, when you're focusing on the answer, sometimes kids only write the answer and you get it wrong. So you got to you got to show work. Essentially, they're telling you to show work. So let's go. Q equals MC delta T, right? All right. So it says calculate the Q. So Q is what we're looking for. And then let's go to M. M is 120.0 grams. All right, we have a problem. We don't have a C, but that's where the water comes in, right? Remember water? So if we go to, again, and do you notice that they're making you go from the beginning of the reference table to the end of the reference table? This is why I said, try to memorize some of this, right? Like either one or the other. So you either memorize the specific heat capacity of water and the STP values, or memorize Q equals the equations, right? Because then it'll save you in back and forth from beginning of the reference to the end of the reference table. But specific heat capacity of water is 4.18 joules per gram Kelvin, right? So that is 4.18 joules per gram Kelvin. And our delta T was what? Delta T, remember, now by looking at it, we know it's in Kelvin, so we can't use this, right? So we gotta convert this over to Kelvins. And what is that? TI becomes 23.0. How do you get to Kelvins? Plus 273, right? Right? If you don't know, again, right? Look what they make you do. Go all the way back again, right? Again, they're trying to waste your time. And it's right here, right? So don't fall for that. Try to memorize it, okay? All right, so that gives me 7, 8, 9, 296. By the way, I didn't pre-solve any of these problems, so just keep your eyes open. All right, here we go. So final temperature is 86.0 plus 273. Now, to follow sig fig rules, right? It's 273. So technically speaking, it should be no decimal places, right? But who knows, right? So 6, 7, 8, 9, 15, 353. I think that's correct, all right? All right, so take those two values and let's move it over. So we got TF is 359. minus T initial is 296. Okay, I'm going to solve for that, right? And that gives me 63 kelvins. Now we can plug in our values. Q is equal to mc delta T. Let's go. M is 120.0 grams. And you know what? I was stupid because, well, I'll tell you in a second. 4.18 joules per gram Kelvin. I was stupid because I didn't actually have to solve that. You know, I could have, like here, 63 kelvins, that's fine. This is a correct answer. But, you know, I just wasted time in my calculator, didn't I? Right? Because I could have easily, because they don't want the answer. They set the setup. So therefore, what I could have also done was this. Right? I could have done this and it would have been just as correct. Okay? Either way works. Okay? Let's go to 57. State how the molecular motion of water molecules in the beaker changes as the temperature increases. Motion. Well, I think you guys should all know how to do this, right? Right? The motion, what happens when temperature goes up? Increases as temperature increases, okay? Moving on, 58. Nitrogen dioxide gas, NO2, can reach equilibrium with dinitrogen tetroxide gas, N2O4, in a closed system. At 1 atmosphere, the boiling point of N2O4 is 21 degrees Celsius. The equation below represents the system. Compare the rate of the forward reaction to the rate of reverse reaction when the system is at equilibrium. You do realize, literally, they asked this on every single free response question. So please don't disappoint me and let me find out that you didn't watch any of these videos, because this is been 5 out of 5, right? So far, I think. Is it 5 out of 5? 4 out of 4. Whatever, how many? Yeah, this is 5 out of 5, right? 5 out of 5. It was the same exact question they asked you. And what is it? Same rate, right? And it was the same question, same answer. So you just should not be getting this wrong, right? The rates are the same. Okay? State how the equilibrium shifts when the pressure in the equilibrium system is increased at a constant temperature. So what do we know about pressure? If you increase pressure, right, they like side with less number or mole of gas. All right, so let's go look up here. What do we notice? We got 1 versus 2, right? So which side is going to be favored when you increase pressure? It's going to favor the side of the equation that only has 1 gas molecules, right? Because remember, these are both gases. So therefore, what's going to happen, guys? Which side is it going to be favored if you increase pressure? Left or the right side? Right, it's on the right side, right? So let's see how we're supposed to state how the equilibrium shifts. Okay, so just say the equilibrium shifts to the right. You don't have to explain that, right? I explained that, but you don't have to write that down. All right, so number 60, compare the entropy of a sample of dinitrogen tetroxide gas. Entropy, right? What's entropy? Remember, it's the chaos, right? Or disorder. At 25 degrees Celsius and 1 atmosphere, this is condition 1, to the entropy of the same gas at 15 degrees Celsius and 1 atmosphere. So what happened? No change in pressure, but what happened to temperature? Temp went up or down? Right, it went down, right? So it got what? Hotter or colder? It got colder. So if it gets colder, what happens to molecules? They move further apart or come close together? Try to answer these guys, right? Don't just watch this video like, with your mouth open, right? The temperature went down, which means what? It's getting colder, so the molecules of gas is going to come closer, right? So when they come closer, are they going to be more chaotic or are they going to be more ordered, right? Think about it in kindergarten. And then I know some of you right now, I just said that, and then you just randomly just said, oh, you just said an answer. Don't do that, right? Remember I told you to stop doing that, okay? So think about a kindergarten class, right? If the children are far apart or you bring them in closer, which is more ordered, right? When things are chaotic when you're babysitting a bunch of kids, what do you do with them? Let them run further away, or you bring them close and and tight, right? So when it gets colder, things come tight closer. And what does that mean? That means there's more order, right? Right? So you have to see compared. So it's more order. So entropy is lower at the 15 degrees, right? At the lower temperatures. At 15 degrees Celsius. Okay, that's it. 61. Let's keep going. All right. When a solid copper is placed in an aqueous silver nitrate solution, reaction occurs as represented by the equation below. State the change in oxidation state of copper in this reaction. All right. So, this is our jam, right? You know how to do this, right? Let's do it. What's that? That's 0, right? What about here? Well, if you've been doing what I asked you to do, right, optional, is that you should memorize what copper is. Copper is +1 or +2, right? Remember I told you some of the kids should memorize this, especially, excuse me, if you're trying to get into my AP class next year, you really should know what copper oxidation state of coppers are, right? It's +1 or +2. All right, so think about this. What is this? This is +2, right? How do we know that? Well, NO3 is -1. If you memorize that, hey, great. But if not, look what you have to do. You have to go here. You have to go to nitrogen, which is table E, even if you remember that, right? Or not nitrogen, nitrate, and find out that it's -1, and then come back here and be like, well, that's -1, but there's 2, so therefore this is -2. Look how much time you're wasting, right? So it's 0 to +2, right? It's 0 to +2, right? Okay, let's go to 62. Based on table J, state why copper reacts spontaneously with silver, right? Guys, you don't even have to go to table J, right? Because what did they tell you? They told you it's spontaneous, right? What does it tell you about J, copper in table J versus silver, right? It's higher, right? Right. And on top of that, remember what I told you, right? I said silver and gold are on the lowest, right? All the way in the bottom, and you should try to memorize that. So we know already that copper is spontaneous, so therefore table J is what? Spontaneous on top. So I'm not even going to go to the table. I'm going to say, right? Copper is higher in table J than silver, right? And if you don't believe me, right, we can waste the time and go take a look, right? Copper's here, silver's here, right? All right, 63. Write a balanced half reaction equation to represent the reduction of silver ions to silver atoms. It couldn't get any easier, right? I mean, they literally told you what to do, right? So let's go up here, take a look, silver ion, right? And we just said that nitrate is -1, so silver ion is Ag plus, right? And you got solid silver, right? So that's it. So we're doing reduction. So let's go. You're going silver plus going to silver, and what do we say? It's going solid, and this is AQ, right? All right, how do we balance this? Well, you balance it by putting electrons on the left side, right, to balance the +1. However, you already know it says reduction, right? Reduction means what? Ger, right? So therefore, electrons being gained, so that's the answer. During lab activity, 15 milliliters hydrochloric acid is exactly neutral. Okay, so what do we know? We see hydrochloric acid, right, and sodium hydroxide, right? We get an acid and a base, right, guys? You should know that. So therefore, what do we got going? We got a volume of acid, right? And look what I'm doing. I'm already identifying different things in the problem, right? And this is volume of the base. And this is what? This is the molarity of the base, right? You realize I didn't even finish reading the rest of the questions. I highly recommend you don't do that. You read it, but I'm just going to move on. Look, write the name of the procedure used in this activity, right? What is it called, guys? Right? What is it? What do you think? It's titration, right? Now, if you thought neutralization, guys, that's the chemical reaction, not the procedure, right? But I'm willing to bet that if you write neutralization, they might even give it to you, but don't do that. Okay, it's the procedure is titration, right? Show numerical setup for calculating the molarity of the HCl. Well, surprise, surprise, right? So we have it all set up already, right? Let's go. So we got Ma, Va, Mb, Vb. Have you noticed something? This FRQ, they never wanted you to calculate the final answer, right? I mean, you can, like I said, right? So let's fill these in, right? So Ma is what we're trying to look for, right? Because, right, of the acid, that's Ma, right? So let's go. Va is 15 milliliters and 18.2. 15 milliliters. And then this was 18.2, right? And then what was the molarity of the base? It was given to us as 0.11. Right now, do you have to convert this to liters? You don't have to, right? Watch this. It's MAVA equals MAVUP, right? And again, if you have to go look at this reference table, again, you're not studying enough, right? Come on. There's no reason why you should have to go back here, waste your time, look it up, and then go back, right? You are wasting major time if you do that, right? So the equation is here. So let's go. Ma is equal to Mb Vb divided by Va, right? Now, let's plug this in. We got an Mb, which is 0.11 molar. Vb is 18.2 milliliters all over 15.0 milliliters. Now, what do you notice? The milliliters cancel themselves out, right? So it's never a problem, right? And if you notice, if you convert it to liters, you'd be multiplying, dividing both top and bottom by 1,000, which means it's going to cancel out anyway. So this is your correct setup. Now, if you did go ahead and convert this to liters, that's perfectly fine. If you converted this to liters by dividing by 1,000, and I'll use a different color, right? Okay, if I can get a different color, what just happened? Interesting. Where's my what? Okay. So let's shift to a different color. Let's go to purple, right? So if you actually did this, right, 0.015 liters, and then you converted this by dividing, right, and did that, and then if you wrote this, like this, right, that is also correct. That's a liter, by the way, okay? Either way works. All right, onwards. Let's go to 60. All right, so the other thing I like to do is, remember, try to cross it out so that you know which one, if you're skipping any. Base your answer 66 to 69 on the information below and your knowledge of chem. Several elements are considered endangered because there's a risk of these elements becoming unavailable for commercial uses in the next 100 years. I was going to say helium. Remember, I talked about it in class because of Amazon, right? Look at that. Here it is, right? Right. Helium, zinc, gallium, indium, tellurium are included in the list of these endangered species. Number 66. Identify 3 endangered species in the passage that are classified as metals, right? Again, this has nothing to do with what what these guys are, right? You know already that helium is what? That's a gas, so that's out. Zinc is a metal, check. Gallium. Do you know what side it's on? It's on the leftmost side, right? Second column, I think, right? Mr. Kim, should I memorize the reference table, the periodic table? Yeah, you bet, man. Why not? So let's go here, right? Gallium, right? Where's gallium? No, I said second column. No, Mr. Kim didn't memorize it. But what is that? It's still what? See the stairs? It's on the left of the stairs, right? That makes it a metal, right? So there's gallium, right? And then what else? So that's a metal. Check, Ga. Indium, right? That's right around there too, I think. Right? Right here. That's a metal, right? And then what else? Tellurium, right? Tellurium is also in that group. It's down below, right? Somewhere here, Tl, right? So these are all metals. So it says how many? 3, right? So it's everybody but helium, right? Because helium is gas. So if you think about it, you don't even need to go to the reference to the periodic table, right? Because you could have figured this out by just knowing that helium is a gas, right? So what do we got? We got gallium, indium, and tellurium, okay? You can write that out, right? If you don't know the symbols. Explain in terms of electrons why gallium and indium have similar chemical properties. Hello? Gallium and indium, they're in the what? Same what, kids? What do you think? Same group, same family, right? So what do we know about their electrons, right? Who are we talking about? Gallium and who now? Indium? Yes. So gallium and indium both have the same numbers of, be careful, not electrons, it's valence electrons, right? Their total electrons difference, right? Or if you really wanted to know, you could go here and if I erase all this junk, right? You can tell that they both have 3 electrons. So you could have even written down they both have 3 valence electrons, okay? Instead of saying same numbers valence electrons. But my point is number 67, I don't even need to go to the periodic table. I can just say they have the same number of valence electrons because when I was looking at number 66, I already knew that they're in the same family, okay? All right, 68. Compare the density of sample of helium at STP with the density sample of tellurium. Hello, right, guys? Gas versus metal, right? Both at the same temperature and pressure. What do you think? Who's going to be more dense or less dense, right? Helium is less dense because it's a gas, right? So say helium is less dense than who? Tellurium? Tellurium. We're done. Let's go to 69. Explain in terms of what? In terms of electron shell. So I'm gonna put a box around it because what does that mean? When they say in terms of electron shells, right? Put a box. I must use this word. Okay. So why the atomic radius of an atom of indium is greater than the atomic radius of an atom of gallium when both atoms are in the ground state? All right, so let's go quickly take a look. Indium versus gallium, right? So indium versus gallium, right? Ground state. So let's go look at their electron configuration. Indium is what? So what are they asking? A radius for an atom, right? Hey, what do you notice about indium versus gallium, right? What do you notice? And please don't say something like a little too obvious, like, oh, the same number of valence electrons, right? Because guys, think about it, right? We already used that answer. So that wouldn't be the same answer, right? So the answer is what? Indium has more number of shells, right? Look at all these orbits, right? So, um, right? Indium is greater because why? Why is indium fatter than gallium? Because it has more shells, right? Look at that, right? Look at that. So you would write here, indium has more numbers of electron shells, right? Or orbits. Let's go to 70. The Oswald process is an industrial method to produce nitric acid used in the manufacture of fertilizers. Several steps are involved in this process. In the first step, ammonia and oxygen react in the presence of a catalyst as represented by unbalanced equation 1. In the second step, nitrogen 2 oxide reacts with oxygen to produce nitrogen 4 oxide, right? Good to know, right? Represented by the equation 2 below. All right, I'm going to quickly take a look that they're both regular arrows, that it's not equilibrium or bidirectional. Determine the percent composition by mass of nitrogen HNO3. What does that mean? Guys, this has absolutely nothing. This question, number 70, has absolutely nothing to do with this, okay? So that's what I want you to know. All right, so let's go. And again, you should know the formula, right? Formula is what? Oxygen over whole times 100, right? And if you forget, again, right? Let's waste time, right? You know, I'm sorry if I'm making you feel bad because you're like, oh, I didn't memorize it. I'm telling you right now, dude, just memorize it, right? Right here, percent composition is right here, right? But what did I just say? Mass of the part, which is all of the oxygen over the whole, right? So let's go over here, right? Now, they want the percent composition, right? So it's the oxygen over whole, HNO3, okay? So, well, first of all, they even gave you the whole thing, right? So, I mean, how easy could this be? Now, what is it? It's how many oxygens in here? It's 3 of them, so it's 3 times each oxygen is what? 16, right? Divided by the whole thing is 63 times 100, okay? Guys, it's that easy. So it's 16 times 3, right? Divided by 63, right? Is that I'm just going to do it again. 16 divided by 21 gets the same answer. Do you know what I did? Someone tell me what I did. Remember, 3 goes into 3 once, 63, 21 times, right? Doesn't matter. But in the end, what is the answer, right? The answer we get is, how many sig figs? It got 3 right here, 3 sig figs. And then I assumed 3 sig figs, right? Because I pulled it from the reference table, the oxygen. So I'm going to keep my answers to 3 sig figs, which will be 76.2%. Okay, so I'm going to go over here, right? 76.2%. Also, once again, please make your periods decimals legible. All right. Before I even go, what am I doing? I'm probably going to balance this, right? Let me take a guess. Balance equate, surprise, surprise, right? So let's go. Let's balance this, right? So can we eyeball balance this? Sure, we can. We got 1 nitrogen here, 1 here. So let's leave that alone. You remember oxygen, but it's by himself, so we leave that alone. Do that last. All right, so let's go tackle hydrogen. You got 2 here, 3 here. So if I put 2 here and 3 here, you're going to have 6 hydrogens in both sides. Now, what's the problem? We changed nitrogen. Now nitrogen is 2, so we're going to have to come back and put a 2 over here, like that. Now let's look at what's happening with the oxygen, and then we're going to use the O2 to fix everybody, all right? So let's go. So we got 2 oxygens over here, plus 3 oxygens, that's a 5. I already know that I'm going to have to erase this and do it over, right? Because I got an odd number, right? So how do you get 5 oxygens? 5 over 2 will give me 5 oxygens, right? So what do? We got to multiply everybody through by what? 2, right? So that becomes a 4, that becomes a 5, that becomes a 4, that becomes 6, right? So this is probably why it's probably better to do it separately and not do it directly on the booklet itself. 4, 5, 4, 6. All right, I'm going to give you another word of advice. When you do balance equation like this, go back. Please go back and double check, right? Like not right now, but when you're done with the exam, instead of just waiting for the time to go home, right? Go back and say, okay, using these numbers, does that work out? Let's take a look. We got 4 nitrogens left, 4 nitrogens on the right. You got 3 times 4 is 12 hydrogens, and you got 2 times 6 is 12 hydrogens. You got 4 plus 6 is 10, 2 times 5 is 10, right? Again, the check, do it at the end of the test, right? All right, so let's go to 72. Show a numerical setup, again, numerical setup, right? For calculating the grand formula mass of NO2 produced in equation 2, right? So grand formula mass, but it's grand formula mass, guys, right? Right? Hello. NO2 is what? It's NO2. So what? So N is what? 14 and change, right? 14.01, is it? Or 14.1? What do you think? It's 14.01, right? And it's 16.0, right? So it's going to be 14.01 grams per mole plus how many oxygens? 2 times 16.00 grams per mole. Does suffix matter? Yes and no. I mean, you could actually put the full number, right? 14.0067 and 15.9994. It should be okay, right? That's it. You know what? Again, no calculator, right? We're done. Let's go. Determine the number of moles of oxygen required to completely react with 4 moles of NO in equation 2. So equation 2 is right here. I'm going to rewrite it over here so I can work with it, okay? Now, we don't really need the heat part, but let's go. So moles of oxygen required, that's what we need, but we have 4 moles of NO. You guys remember when I was in class, I used to use different colors, right? For good old sake, let's do that again, right? So what do? Coefficient ratios, right? And what is it? It's dimensional analysis, right? So we're starting with what? We're starting with 4.0 moles of NO. And you got to multiply this by a factor that's going to give us moles of O2, right? So what do? We need moles of O2 here, and you're going to cancel moles of NO. Where'd you get those numbers, right? 1 to 2. You remember? This is called coefficient ratio, right? So now determine the number of moles. They don't want the setup. 4 divided by 2. Seriously, are you reaching for a calculator, right? It's 2.0 moles, right? So let's go. So you got to go over here and put 2.0. What happens if you forget the 0.0? I don't think it's going to matter. Let's go to 74. 74. As plant grows, light energy is converted into chemical energy during the process of photosynthesis. The reaction produces glucose and oxygen to balance the equation of. So again, you know what? All of this, they're wasting your time, right? They're scare you because they figure, hey, kid, remember you forgot all your photosynthesis from living environment. They're trying to scare you, right? Don't worry about it, right? Here we go. State the molecular polarity of each of the reactants in the equation. I mean, come on, carbon dioxide. What do we know about carbon dioxide, right? If you don't remember carbon dioxide, right, you should memorize that, right? Right? First of all, what's water? Water is the poster child of what kind of molecule? Polar bears dissolve in water. Therefore, what's water? Polar. Polar covalent, right? What's CO2, right? Look, all of these are non-metal and non-metal, so therefore they're all what? They're both covalent, right? Right? Don't write ionic. There's no metal in here, right? But what do we know? We know H2O is polar covalent. If you really have to guess, what do you think this is? This is probably non-polar, right? But if you draw the Lewis diagram, right, when you finish, it's going to come out like this, right? Like that. And what do we know? It's symmetric. Remember, if the molecule itself is symmetric this way and that way, then it's non-polar covalent, right? That's how we do this. All right, let's go. 75. In the Space and the Airs booklet, draw a Lewis electron diagram for a molecule water. Like seriously, just memorize water, guys. They ask you so many times. Water is this. Okay? We're done. All right. I don't even think we have to circle that, but you know what? There it is. Based on table S, compare the strength of attraction of a carbon atom for electrons with the strength of attraction of oxygen atom for the electrons in a bond between them. Well, first of all, what do we know, right? Guys, we can actually do this without the reference table, right? Think about it. Leo says Gur, right? What's oxygen? Losing electrons, right? So what does it tell you about strength of oxygen for pulling electrons, right? Right? So you remember oxygen is the best oxidizing agent. That's why it's oxidizing agents named after oxygen. So oxidizing agent means what? It's causing everybody else to lose electrons, right? Or if you're metal, you lose electrons and then you become rusted, right? Like, iron oxide, right? So you know that oxygen is going to pull electrons off from somebody else, which means that oxygen is king of taking electrons, right? So you can say oxygen has stronger attraction, right? To electrons than carbon, right? Except now, if you're thinking, well, what if you don't know that, Mr. Kim? Like, go to table S, right? But like I said, guys, it's a waste of time, right? That's why, I taught you guys to try to not to use this as much as possible, right? So what do we know, right? Well, first of all, guys, even if you don't use table S, you got to know the definitions, memorize the definitions of these two, okay? Out of these two, which is the one where it's the strength of electron being pulled, it's this one, right? Right? So let's look at electronegativity, right? How much you want to guess that oxygen has a higher number, right? Here we go. Electronegativity of oxygen is 3.4. Let's go to carbon, 2.6. Surprise, surprise, right? So you could actually go to table S, look up electronegativity, and say, okay, oxygen has a stronger attraction because it's 3.4 versus carbon is 2.6. But honestly, you can just write that because oxygen is the king of oxidizing agents. That's why it's named after oxygen. And we know that oxidizing agents, they pull electrons off of everything and everyone, okay? All right, so let's go to 77. And state in terms of element classification. Again, you have to circle this and say, right, use this word. Why CO2 is a molecular compound, right? What is CO2 is a molecular compound? It's element classification. I think this is basically in the end, what is it? A molecular compound is formed by not ionic, but polar covalent, right? So ionic compound is formed by metal and non-metal ions, but covalent compounds make molecular compound, right? So, and then what else we know about CO2? We said it's non-polar covalent, right? So you can write because CO2 is non-polar covalent. All right, let's go. 77, we're done. 78, write the empirical formula for glucose. All right, like seriously, how easy is this, right? C6H12O6. What is it? That's the molecular formula. The empirical formula is what? CH2O. So I'm gonna go over here, right? CH2O. Now, while we're at it, though, right? You know how to solve from molecular formula. I'm sorry. You know how to calculate the empirical formula, right? You remember the poem: percent to mass, mass to mole, divide by small, multiply to whole, right? You should still review that because there could be a chance that they ask you, right, in the multiple choice. All right. Based on the answers to some of the blah, blah. In the United States, nearly all fuel for automobiles is a mixture of gasoline and ethanol, C2H5OH. The equation below represents the reaction between ethene and water to produce ethanol. All right, so this is ethene, right? And that's water. All right, now let's go. State the class of organic compound to which product in the equation belongs, right? Well, guys, do you know this? It's a double bonded carbon, right? Which is it's an ene, right? What kind of ene? Alkene, right? If you don't know, you can go here, right? Right? They literally use the same one from the reference table. Now, remember, guys, this is from June 2023. So in the actual exam from 2 years ago, they literally used the same one as the example, right? And what's a class of compound, right? The name is, it's an alkene, right? So it's an alkene. State in terms of carbon-to-carbon bonds, why the hydrocarbon equation is unsaturated. Hello? Right? Right? What do we say? Carbon to carbon bond is what kind of bond? Guys, come on. What kind of bond? Double bond. Okay. All right, let's go to 81. Identify the element in the product of the reaction that allows it to be classified as an organic compound. All right, first of all, there's only one right here, right? What do you notice, guys, right? It says organic compound, right? I mean, do you need to go anywhere with this? Guys, whenever you hear how to identify as an organic compound, what do you write? Right? Memorize that, okay? Remember? So this is another one that actually shows up over and over and over and over and over. Almost like I think like four out of 5 tests so far. They ask, how do you know it's organic? And the answer is, carbon, right? Let's go to 82. We're almost done, right? And think about how easy this is, right? It's not that bad, right? Right? Oh, because you covered everything, Mr. Kim. Oh, thanks, guys. All right, and laboratory activity, student measures pH values of the household liquid shown during this. Okay, again, safety was used. Okay, I get it. Whatever. All right, so let's keep on. All right, we have different pHs, right? Let's go. Identify liquid tested by the student that is most acidic, right? Who's the most acidic? What do we now write it down here, right? What am I looking for? Highest pH or the lowest pH? What do you think? It's the lowest pH, right? And who would that be, kids? It's right here, right? So I would write down lemon juice. All right, let's go. State the color of the Bromcresol green after the indicator is added to a sample of lemon juice. Okay, it's acid, which means what? Low pH, right? Bromcresol green, right? Oh, I don't know. Is it green or is it Bromcresol? That's a joke. I know it's not funny. Here we go. Bromcresol green is what? Yellow to blue, right? Low is yellow, right? Right? It's yellow here, blue here. So since the pH is acidic, it's yellow. So you write yellow. All right, let's go. Number 84, complete the equation in your answer booklet by writing the formula of the missing product of the reaction of aqueous potassium hydroxide with vinegar acetic acid. Well, first of all, guys, even before we go there, what's this? This is base, right? Right, KOH, and then what's what? That's an acid, right? Base plus acid is what? Neutralization, right? Which gives me what? Something and what? Water. What's this? This is salt, right? Ionic, right? And remember what we said, right? Neutralization is a what? Is a type of, oh, are they joking, right? Base plus acid gives you salt then. They literally asked you to identify the easy one, right? 85. based on the pH value in the table, compare the concentration of hydronium ions to concentration of hydroxide ions in the distilled water, right? Hydronium ions in the table, hydronium to hydroxide. See, here's what happened. That's a trap, right? They're trying to confuse you, right? You don't need to do that. Okay? They're looking at distilled water, right? Is it acidic or basic? Right, it's neither. It's neutral, right? If it's neutral, what is this pH? What do you think? 7.0, right? Hey, I have a question for you. In the same solution, if the pH is a value here, what's pOH? pOH is what? How do you calculate pOH if you have pH? What do you think? Right, it's 14 minus 7, right? Hey, surprise, surprise, it's 7.0. So we know that in neutral solution, both pH and pOH is 7, right? So what do you say? Both pH and pOH are, oh, that's not how you write it. That's PO, like Winnie the Pooh. That's not a thing, Mr. Kim. I know, it's pOH, right? Are the same, right? 7.0, right? You can say they're both 7.0. You can write they're the same, right? Hey, let's continue. And guess what? We're yet done with another one. And it was that easy and that much fun. And so I looked online and it looks like the last video, only 15 people looked at it. So I don't know, man. I'm pitching, right? I hope you're catching or watching. All right. So hopefully I'll get another one soon. But until then, I will see you guys back here on this channel. Peace out.